Welcome everyone to the Planetary Science plenary session with our named lecturers. Please sit down, and my name is Sarah Stewart. I'm the outgoing president of the Planetary Science section. I welcome you to the Planetary Science prize lectures and awards. We will begin with the Shoemaker lecture, and Rosalie Lopez will give the introduction.
Good evening. It's my great pleasure to introduce my colleague, Carol Raymond. Carol is the Dawn principal investigator. She's also a principal scientist at JPL. She received her PhD in geophysics from Columbia in 1989 and came to JPL shortly after. She was the Dawn deputy PI and later became the PI. And she's also PI of the IceMag instrument which is in development for the Europa Clipper. She has over 200 publications on Earth tectonics, ice sheet history, magnetic fields on Earth and Mars, and evolution of Vesta and Ceres. She has received many awards. She's a fellow of the Geological Society of America. She received NASA's Exceptional Achievement Medal, also the Antarctica Service Medal, and she even has her own asteroid 10724 Carol Raymond, given in recognition for her work on the Dawn mission. So now you get one more certificate. Please help me welcome Carol Raymond.
Thank you, Rosalie. Can everybody hear me okay? Okay. Loud and clear. So I guess I'm going to hang close to the microphone here. So I'm thrilled to be presenting today the results of the Dawn mission. As many of you probably know, the Dawn mission ended on November 1st. So in addition to sharing all the wonderful results that we obtained, I'll consider this a celebration of life for the mission. Okay, so I wanted to start by saying that I'm truly honored to be giving the Shoemaker lecture because Gene founded the discipline of astrogeology and was a leader in the exploration of the moon. And he and Carolyn were very prolific observers and discovered many comets and asteroids. And I really think Gene would have been fascinated by the results of the Dawn mission at Vesta and Ceres. And so I'm really honored to be sharing them with all of you. So let's get started. So the Dawn mission was conceived as a journey back in time to the dawn of the solar system to investigate the conditions and processes which were occurring. The targets were Vesta and Ceres. These are the two most massive objects in the main asteroid belt. And it was selected in 2001 as a discovery mission under the leadership of Professor Chris Russell at UCLA. I've only recently become the PI during the extended mission phase. And it's a collaboration of many partners that built and launched and operated the spacecraft. And the logos of our partners are on the bottom, and I'll be pointing out later some of their contributions. But suffice it to say that the mission could not have been as successful as it was without these partnerships. So just a few background slides for those who may not already know all this stuff. Vesta and Ceres are located in the main asteroid belt, which is between the orbits of Mars and Jupiter. And they are in different parts of the asteroid belt. So if you look at the plot of the radial distribution of asteroids with heliocentric distance, you see that Vesta's mean orbit is about 2.4 AU, or 2.4 times the distance of the Earth and the Sun. And Ceres is a little farther out at 2.8. And so they're quite close together, relatively speaking, in the solar system, yet they straddle a boundary between a much drier part of the solar system and the beginning of bodies that still contain abundant volatiles. So that made these two particularly interesting targets for the mission. I said they were the most massive. Here we see them as we knew them through the Hubble Space Telescope lens before Dawn went to take a closer look. And I'll just update that we now know that these constitute 45% of the mass of the entire asteroid belt. So there's a lot of material incorporated in these bodies to tell us about those early days. So the main questions that were asked, or the bigger questions in planetary science that we're trying to answer with this mission is what was happening when the nebula was developing, the sun was forming, and there was abundant radioactive heat. And during the time that there was this abundant heat, the bodies forming would have incorporated that. So the questions are, what chemical gradients were already existing in this nebular disk? How did the formation time of the objects affect the outcome? And then how did these bodies evolve and migrate post-formation? So this motivated our mission to go to Vesta and Ceres to try to answer some of these fundamental questions about protoplanet formation and evolution, including the role of size and accretion time, differentiation and interior evolution, the role of the initial composition and the overall accretionary environment, and then how did impacts affect and change these bodies as they aged. So here's a bit of a roadmap for the mission. I'll just point out a few of the events. We launched in 2007 from the Earth. We passed Mars and got a gravity assist, and we arrived at Vesta in 2011. And we spent 14 months at Vesta in orbit, and then spent 2.5 years thrusting out to reach the orbit of Ceres, where we arrived in 2015. And I'm skipping off of Sarah's head. and then we spent 3.5 years at Ceres, going through aphelion and around through perihelion until the mission ended in October. So in addition to answering or attempting to answer all these big questions, there's really nothing better than the thrill of exploring new worlds. And again, these bodies presented us with new landscapes and new landforms that we could not have conjured up ahead of time. We knew quite a bit about the objects, which I'll be talking about, but there were just so many interesting things that were revealed by going there and actually taking a look at fairly close range. So on the left is Marcha crater, one of the snowmen craters on Vesta. Very interesting crater in and of itself. And then here's an example from Ceres of Hylani, a very young crater that has many compositional variations and morphologic features that they're quite interesting. So overall, Dawn's exploration has informed us about the geology, geochemistry, geophysics, about impact fluxes and the effect of impact processes on these bodies, their links to meteorites, differentiation, and exogenic volatile delivery. So it's quite a bit of information that we've gotten through this in situ exploration. And to perform this investigation, we brought three, so a small number, three very capable instruments, and they were contributed by Germany, the framing camera from DLR and Max Planck, the visible infrared spectrometer from ASI and ENAV, and our gamma ray neutron detector, which was built at Los Alamos and is now being led out of Planetary Science Institute. In addition to the instruments, we use the spacecraft, the coherent Doppler tracking, using the radio system to get the gravity data. And we also use the camera to derive topography. Okay, so what did we know before we went? We have a lot of information about Vesta because we have many, many meteorites that come from Vesta, the Howardite, Eucrite, Diagenite series. And eucrites are like very basaltic in composition. Diogenites are a deeper seated lithology, more like a gabbro. Cumulate eucrites were slower cooled, and howardite is a brecciated mixture of all of the eucrite and diogenite. So it's probably no surprise on a body that's 4.6 billion years old that there's mostly howardite on the surface. It's a very battered surface. So stimulated by the Apollo era, Tom McCord, Torrance Johnson, and John Adams decided to see if they could match telescope spectra of bodies to meteorites in the lab that had been studied. And so they started a project to do a systematic study, and here this spectrum on the top shows the spectrum that was obtained of Vesta that matched those of the HEDs, which are shown here on the bottom. This was a really confident match, and they thought, this is great, we're off and running. And then that was about it. There were no more confident matches to bodies. So Vesta is very special in the sense that it has a very unique spectrum, and it's associated with lots of material. So we have many, many meteorites to study and understand its internal evolution. Okay, so this is what we knew of Vesta's surface before we went. This is the results from the Hubble Space Telescope. You can see we knew there was albedo variations, in particular a very dark region right here. And there's a bite out of the southern hemisphere showing a deep basin with a little mountain in the middle. What did we know about Ceres? So I wanted to just take a little sidetrack on stories about Giuseppe Piazzi, who discovered Ceres in 1801. He was looking for the missing planet between Mars and Jupiter as not an official member of the Celestial Police, but one who was following in the same track. Because they believed there was a planet that should be there, and they just needed to find it. So they found Ceres and thought they were all done until, of course, many, many more asteroids were discovered, and it was realized it's a belt of material. But he found it, and then he lost it due to bad weather. And then Carl Friedrich Gauss had just begun to make very precise measurements of orbits, and he managed to calculate the orbit and tell everybody where to look, and they found it again. So in 2004, Hubble trained its lens on Ceres and returned these data. And here you can see, yeah, there's a couple of bright spots in there that look interesting. And from the shape of Ceres, we could tell it was volatile rich, had a hydrostatic shape. And now here in 2015, we've returned these incredibly detailed portraits of what this object looks like. And I just wanted to emphasize that this is a fairly short time frame to have gone from discovery to knowing so much about this body. Okay, so let's get into it. Here you're looking at the two bodies with their relative size. Sorry, the relative sizes are shown here. And you'll notice this is the topography, and you'll notice the scale here for Vesta is about over 40 kilometers in relief, whereas for Ceres is about 14. So we see that Vesta is a very rugged body, and it's got a fairly varied topography. Ceres is smoother and has some deep basins and a heavily cratered surface. And that's not something we were expecting, because we knew that Ceres would have retained a lot of ice and expected there's an icy crust on the outside and we wouldn't see a lot of craters. But we did, which was wonderful because it told us something about the interior. Okay, so what did we learn? Now I'm getting some echo. Is that bothering anybody? Okay. So what did we learn? We confirmed, based on the predictions from the HED studies, that Vesta is volatile pore. It's fully differentiated into core mantle crust, and it is the parent body of the HED meteorites. We also learned that it formed from volatile depleted material, experienced a complex magmatic evolution, and also accreted impact-delivered volatile-rich material. And the last point was quite a surprise, and I'll be talking about that later. For Ceres, we confirmed that it was volatile-rich, partially differentiated, and had experienced global aqueous alteration. These were, as I said, predicted from the Hubble data and also from modeling that had been done based on that. So what we learned is that Ceres is ammonia-rich. This was suggested by some infrared spectra from the ground. That was shown to be true. It's similar to, but not a match to, an altered chondrite, CI, and has ongoing brine-driven geologic activity. So, these two last points on the bottom are the real surprises that we found that were not predicted. So here's the evidence for the match between Vesta and the HEDs. You see in the two pyroxene bands of the Beer spectrum, as well as in the elemental ratio plot on the right. So the fields of the HEDs are shown by the dots, and the gray region here and the ellipses are showing you the dawn data. So this was a very confident match, and also showed that the data are dominated by Howardites. And as I said, again, it's not unsurprising because we are looking at the surface. Now recall the gamma ray neutron detector can penetrate about 1 meter into the subsurface, whereas the spectrometer is only looking at the top millimeters. Now we also could infer from the gravity and topography data that Vesta indeed has a metallic core. The shape and the gravitational J2 moment is consistent with a core of a radius about 110 kilometers, and if you assume a core density that matches iron meteorites. And this is consistent with metallic element depletions in the HEDs, which was one of the lines of evidence arguing that Vesta had a core pre-dawn. And also the core mass that we measured is consistent with what those models predicted. So again, this was a nice validation that the pre-dawn models were correct. Now, if you take that constraint that we measured here for the core density, core radius family of solutions shown in this gray bar, and then compare it to the calculated values for starting composition of different chondritic precursors, and calculate out how the body would end up, you find that many of them don't fit, and the two that do are an H chondrite, a relatively volatile pore, and a CM, a smaller percentage of CM chondrite, and that gives us a good fit to Vesta's constraints. Also, the thermochemical modeling has shown us that Vesta must have formed within about 1.5 million years after formation of CAIs, and likely had a shallow magma ocean. So I told you we already knew there was a large basin at the South Pole from Hubble. What we found was that was not one, but two basins, one on top of each other. The Venonea being the one underneath is about 400 kilometers, and Rhea Silvia being about 500 kilometers in diameter on a body that has a radius of about 560 kilometers. Sorry, diameter, 560 kilometers. So these are really important for Vesta's evolution, and the fact that it survived these impacts is quite surprising. It also excavated deep into Vesta's interior, and for that reason, one would expect to see a lot of olivine at the surface if indeed we had Vesta differentiated into a basaltic crust, an olivine mantle, and the iron core, which we have inferred. We do not see olivine there, and so I'm going to be talking about that. But we did determine that this basin, which is about 1 billion years old, estimated by crater age dating, is the likely source of all of the Vestoids, which are the family of Vesta, which is co-orbiting with it, smaller asteroids, and the HEDs, which are pieces of Vesta that are drifting into a resonance of Jupiter's field, Jupiter's gravity field, and being sent on Earth-crossing orbits. And that's why we have so much material from Vesta on Earth. So these giant impacts also caused so much stress to go through the body that it cracked it into these giant troughs. And there's two main set of troughs. One in the north called Saturnalia Fossae, and these equatorial set, the Devalia Fossa. And if you take the planes of these troughs and look at the poles, you find that they coincide with the center of these impact basins. So we have a connection between this deformation event and these large impacts. So they likely nearly shattered the object, but instead left these giant scars. Okay, so we're going to switch gears a little bit and talk about then what else we could determine based on Dawn's data about Vesta's evolution. It was known from the HEDs that there's a lot of variation in the trace element chemistry, which had raised the question of whether there's more than one parent body of the HEDs. Are there more than one Vesta-like bodies out there? Melting models predicted that on a body this size, you would not have magma ocean and just have melting in the crust, which could lead to this type of heterogeneity. And then recently, somewhat stimulated by John's data, Mandler and Elkins-Tanton came up with a model that started with equilibrium crystallization in a magma ocean after the crystals become so thick that the convection stops, and then you get rise of the magmas into shallow chambers and fractional crystallization. And this type of sequence can explain a lot of the observations that we have. So what does Dawn's data tell us about whether or not that is a viable model? We can look at the distribution of the eucrite and diagonite, and remember the diagonite is a slower cooled lithology you expect to see lower down in the stratigraphic sequence. And in these two plots, you see what Grand says from the element ratios about the percentage of eucrite and diagonites, eucrite being blue, diagonite being red. And then what does Veer say? Again, same color bar. And what we see is there's this area which is more diagonite rich. It's a little bit less pronounced in the Veer data, but it shows up well in the Grand data. And it coincides with density anomalies in the gravity field, which are shown here, high density being in the red. So this pattern can be inferred to be consistent with plutons, or these late stage magma chambers, which are bringing material into the crust, intruding into the crust, and leaving behind these discrete areas with different composition and higher density. Now, I mentioned hydrogen on Vesta, and here you can see in the same up top from Grand data and here from the Veer OH band, the distribution of hydrated material on the surface of Vesta. It is beyond what you could expect from solar wind implantation, and it indicates the presence of hydrogen from impacting carbonaceous chondrites. And this was, again, quite a surprise that this material could be deposited on the surface and survive over this long period of time. Now, it matches well the concentration of carbonaceous material that you see in Howard ice. So it was not known from the meteorites themselves whether this was a pervasive element of Vestan material, but the concentration that you see in these carbonaceous-rich howardites is consistent with what we're seeing in these areas on the surface. So there also is quite complex geology on Vesta, and this is one of my favorite examples of the light and dark material that coincides, or that exists in close proximity. And here in the color band data, you can see also there's a lot of complexity in compositional variations. And this is just a single crater, but we see this all over the surface of Vesta. So we had, the team had a lot of fun mapping all this stuff. And this crater, Marcho, which I mentioned at the beginning, is a good example of this light and dark material, where you can see that the light material is outcropping here at the top of the crater wall, and then there's a dark layer that is mass wasting down the crater wall at a lower level. And if we can zoom in a little bit and see that a little better. So next you're going to see animation, a flyover of this crater, where a lot of the processes that we mapped are evident. A lot of mass wasting, variation in the texture of materials. We have a lot of rough material, more competent in the crater walls on one side of the crater, and then we have this very smooth deposit over on a bench. And then importantly, here's the bench. Importantly, down in the center of the crater, there's a deposit of very rough terrain, which is pitted. And these pits are increase in size away from a central source, like a vent, and the likely origin is release of volatiles. So this was shown by analogy to pitted terrains on Mars, and again, consistent with the fact that we know we have hydrated material that's been delivered to the surface of Vesta, and here it seems to have been activated by the impact process and led to this volatile release. We also see that in the bottom of another small crater, recent crater, there's a pond of pits here in the bottom. And in this particular crater, we've also mapped these sinuous gullies, which are very different than the gullies you see in many of the other craters. So there's two styles. One are these straight ones that are consistent with dry granular flow, but these sinuous ones are much better explained as a result of transient water flow. So this is something that Jennifer Scully's been working on for quite some time, and she's doing some lab experiments to really try to get a better picture of how this process might have taken place on Vesta, one of the driest bodies in the solar system. And so here's an example of an impacting comet or ice-rich body leaving a layer in the subsurface. So not all of the ice is sublimated, some of it gets trapped. Another impact comes in, melts it, and for a very brief period of time, you could have water before it's all sublimated away. And that would also explain why we have these pits in the bottom. So that's a good place to segue into the findings at Ceres. Ceres being one of these very volatile rich objects, which may be similar to the type of thing that left all of these volatiles on Vesta. So I'm going to go through the major findings, and then I'm going to give you some of the information that backs it up. So as I said before, we believe that Ceres formed with abundant volatile material and subsequently experienced substantial evolution. The abundance of the ammoniated material was one of the key discoveries that we made, because this indicates that Ceres formed in an outer solar system environment. That amount of pneumonia, that amount of ammonia is not stable in the neighborhood that Ceres lives in now. The global alteration indicates a water-rock ratio greater than 1, and this amount of interaction between the water and the rock would have moderated the internal temperature while Ceres was undergoing differentiation, and that left it only partially differentiated. So that's a really important point, because other objects like Ceres in the outer belt, or beyond the outer belt, would have had a similar evolution and could be left with as much volatile rich material as we see on Ceres today. Whereas Vesta, all of the radioactive heating heated it up, melted it entirely, and as we see, there are no volatiles left. Okay, organics were detected on Ceres, but only in one location, and it may be that the surface is organic rich, but we can't detect it because of obscuration by space weathering. And I already mentioned that Ceres, we believe, is representative of a class of large volatile rich bodies, and these have affinities to icy moons in the outer solar system. So just a beauty shot of Ceres in color from the framing camera bands. Obviously Ceres is dark and wouldn't look very colorful if you're looking at it with your naked eye. But here you can see that there are areas that are relatively bluer, and there are these bright spots which show up in these blue areas, and then we have some other large-scale color variations on the surface. So what does the average surface composition look like? This spectrum shows that we have bands which are dominated by carbonates and ammoniated phyllosilicates, and a lot of dark components. So these represent only a few % of the overall mixture, but they are very important to the story of series evolution. And interestingly, the band centers for the 2.7 and 3.1 bands are nearly constant over the entire surface. So whatever event left these carbonates and phyllosilicates, it was a global process. Whereas the band depth has some variation, and in this 3.1 band depth, you can see that some areas are more or less ammoniated than others. Okay, and I said, is a pervasive global alteration consistent with the circulating fluids of this, this initial differentiation? I mentioned already we saw organic rich deposits in only one location. They're also associated with a unique bright red color in the framing camera color data. So our inference is there isn't a lot of this material on the surface, because we should be able to locate other places where we see it in the color data. There are some places that it may occur based on that, but nothing that's as obvious as we see in this Ernitech crater in the north. So this begs the question, with all of this ammoniated material, where did Ceres form? Prior to dawn, there was a theory that Ceres was a captured Kuiper Belt object. And it does bear some affinity to those, but it would be dynamically difficult. And also Ceres does not really resemble TNOs and KBOs. It may have formed from material which was brought in from the outer solar system by gas drag or planetesimal drift. And that would make sense, except that we now know that when Jupiter started forming very early, opened up a gap in the disk, and it would have been a barrier to bringing that material in at the time Ceres was forming. So our current understanding is that Ceres likely formed in the giant planet region, taking advantage of the feedstock that was already there, and then it was scattered during the giant planet growth and migration to its present location. And this is very consistent with emerging cosmochemical models. So this is a hypothesis that's up there to be investigated further. Okay, so that's the surface. Now let's go a little bit deeper. Grand mapped hydrogen and iron, those were very easy to map across the surface. And what we see is that there's a water ice table at the poles. And in the ice-free equatorial region, the composition can be interrogated of the regolith. And so it's shown to be similar to an altered carbonaceous chondrite, a CI or CM composition, except the iron abundance is much lower. So this is consistent with sinking of the metal-rich particles in a global ocean. It could have other explanations, but it fits in very well with the overall story. And then going deeper, we learned from the gravity and topography that Ceres has about a 40-kilometer thick, strong crust. Now remember I said we expected there was a lot of ice and it would have been very weak, but instead it's strong enough to retain craters up to a certain diameter, and it's likely composed of a mixture of rock and ice and salts and clathrates. The clathrates are super important because they give the crust strength, but they're very low density. And so we had to match the density of the crust inferred from admittance with the strength of the crust, which couldn't include too much ice. So we ended up with no more than 30% ice in the crust. And below that layer is a much denser but weak upper layer, which is inferred to have pore space which is filled with residual brines. So the strength decreases, and this is controlling the global shape. Now, we can only see to a certain depth, and then it becomes ambiguous, but the possibility of a dehydrated core at depth can't be ruled out or confidently ruled in. So was there a subsurface ocean? That's a question that was one of the things we wanted to know. And we can say the evidence says from the gravity and shape data that they're consistent with these models that produce an ocean. The ice-rich regolith is indicating this extensive water rock fractionation and volatile mobility. And this pervasive ammoniated material is indicating a global alteration event. So all of those things together clearly support the idea that Ceres hosted a subsurface ocean through a portion of its history. And then the question is are there any liquids or brines available today? Okay. So this is just to give you a pictorial then of Ceres accretion and growth. The ices and the silicates separate, form a differentiated or partially differentiated structure. And then importantly, we lose the sort of the pure ice shell to impacts and sublimation and mix up materials in this outer crust. And then also have some evidence that I will be showing of some hydrothermal activity on the surface. And it's unlikely that this kind of evolution occurs on bodies that are much smaller than Ceres. And there seems to be a limit of several hundred kilometers, maybe larger, where the type of water rock interaction that occurs is not sufficient, is not well enough connected to moderate the temperature and allow this kind of a scenario to take place. Okay, and that begs the question of, is Ceres unique? So this plot is showing from Takir and Emery, showing the diameter of the body versus heliocentric distance and accretion time. And here you see temperature contours and three fields where silicate melts occur, a field where ice is melting, and where ice is stable. And here's Ceres up here at this boundary between silicate and ice melts. It's spectrally similar to Interamnia and Hygeia, but it's not very similar to other asteroids in the Themis class and that are Pallas-like, which look much more like either ice-bearing or CM composition. So it would be interesting to see what Hygeia looks like, but from what we know now, it's not clear that there are a lot of objects like Ceres out there. I keep getting ahead of myself on my main points there. Okay, so finally I'm going to spend the last part finishing up with what's really unique about Ceres. And that's that we find it to be a chemically active world. In addition to finding ammoniated clays on the surface, these bright deposits, this one being the most famous in Okator crater, are dominated by sodium carbonate. And they also include salts, including ammonium salts. And these are very unusual materials in the solar system. They're found in hydrothermal environments on the Earth, this being in California, and also coming out of the plumes of Enceladus. So this is an opportunity to investigate what the processes are that are bringing material from the interior. These materials are consistent with what we expect from the freezing out of the global ocean that we've been talking about. So the carbonates occur in young craters, and they're also associated with cryovolcanic features. We've identified one cryovolcano, that's in air quotes, Ahuna Mons over here. And all of these brighter spots on this plot against a pretty bland blue background are the areas that are carbonate rich. And Ahuna Mons, shown in this inset, is a small mountain that talk more about in the next slides. But here you can just see how rich it is in carbonate by those red streaks. So clearly this material is coming out at various places on the surface, and it's likely weathering over time so that it's not as apparent in older terrains. So Ahuna is a great example of local brine-driven geology, because as I said, it's not associated with a crater. This small crater on the side of it is not sufficient to have triggered this kind of an event. It's a 4-kilometer high mountain. It looks very young. We already saw the streaks of carbonate. And this occurrence of salts in all of these settings is really suggesting there's a near-surface abundance of this brine material. And this feature likely came up as a constructive feature of extrusion of this brine slurry. And the force that was pushing it up is likely some sort of a freezing expansion in the subsurface. So we do know that there are more than one way, there is more than one way to get this material to the surface. And back to the conclusions from the gravity and topography, remember there's a sharp drop in viscosity at about 40 kilometers depth associated with pores that are full of brines, and you can see here the fall off in the topographic power spectral density at that point. And so we have good evidence now that there is pockets of brine in the subsurface, and likely they're existing at grain boundaries. So let's take a final look, as I'm finishing up here, at the most enigmatic and charismatic feature on the surface of Ceres, Okator crater, where the Seralia facula and the Venalia facula lie. Facula is a term for bright material or a bright spot. And this crater is about 92 kilometers in diameter, and the age dates continue to evolve, but it appears to be as young as 20 million years old. And the facula, the Seralia facula in the center, appears to be even younger. Perhaps the youngest age is a few million years old. So there is evidence for recurring eruptive processes in this crater. And the central dome is also sharing a lot of similarities with cryovolcanic features that are found on icy satellites. So in the last extended mission, we put Dawn into an elliptical orbit with a low periapsis at 35 kilometers altitude and targeted the Okator crater so that we could really take a close-up look. And it's too bad the lights are so high. That's a bit better. Yeah. But you can see all this online. So we got an incredibly detailed view of this central pit of Okator crater and the dome and the distribution of the bright material and all of the fractures. And the really interesting thing is that the geologists were all expecting to see flow features and some boundaries here, and they did not see those. So there's a lot of thinking going on about what is causing this uplift, and also whether the material has enough strength to hold on to some of the telltale features of its origin, or what other explanations there are. Up in the corner here, you see the detail of the crater wall and a little bright deposit that's been exposed, and it's just flowing down the crater wall, and we see a lot of stuff like that. There's tons of really, really interesting details in these new data. Here, clearly some fairly stronger component material at the crater rim, outcropping, and lots of other material that's mass wasting. A lot of cracks at every scale. Some of them look like they are reactivated, recently reactivated. And so fracturing is clearly a major process that's occurring to the present day on Ceres. And then finally, this feature over here, which is a deposit that's stranded up on a high-standing ledge of the massif at the edge of this pit. And it's a really super interesting deposit, and you can see a little bit the streaks that are coming down the wall from that deposit. So the Venalia faculae is a series of connected bright spots, and they seem to be associated with fractures. You can see that pretty clearly here. The distribution of the bright and dark materials is quite enigmatic, and here you see one of the most recent features is a very dark feature. Zooming in on it, you see a lot of texture, and the fractures, which I mentioned, which seem to have been reactivated after the bright material was extruded, likely ballistically from venting. And then finally, here's another example where you can see this tiny little tendril of the brightest material just flowing down the side of this fracture. So incredibly interesting geology features on this alien ancient ocean world is just a fabulous mission and a really wonderful set of data, which I think are going to give people lots to think about for long into the future. So I'm going to play a flyover movie and then go to the summary. And what you're seeing here is what we had after our low altitude orbit, and now being played on top of that is the increased resolution data that we collected in our last extended mission orbit. And a lot of features came to view in these very high resolution data, including flow fronts, pits, mounds, the fracture networks, and the relationship of the bright material, as I said, to the underlying crater floor and to the fractures. And now we're going to come up to Cerealia facula. We're going to turn the contrast down, and you can see there's that perched bright deposit on the massif, and here in a perspective view. So let me summarize on what the broader implications of the mission were to try to answer the questions that I mentioned we started with. So Ceres and Vesta do appear to have formed closely in time with similar radioactive material, but their paths diverged largely as a result of their initial compositions. So water-rich and volatile poor. And so Vesta, from Dawn's data and from the interpretation of the evolutionary path, appears to have formed from volatile depleted feedstock, similar to H. chondrites. But volatiles were delivered later by impacts. And Ceres incorporated ammonia, likely ammonia hydrate, indicating it formed likely in the giant planet region and then migrated to its current neighborhood. And Ceres is an extremely interesting object from the perspective of ocean worlds, because now we know about the evolution of an ocean world body, one that is now a frozen ocean world, largely, but still gives us a lot of insights into what may be going on at Europa, Enceladus, and Triton. So to wrap up, we learned Vesta was the parent body of the heads. We confirmed that, and that it underwent a complex magmatic and geologic evolution. Ceres formed later, but not much, likely within 3 million years of CAIs, and it partially differentiated, underwent global aqueous alteration, and has ongoing brine-driven geologic activity. And so we did come to the conclusion that radial mixing in the protoplanetary disk is an important, did take place and was important in the outcome of what bodies formed and how that influences where they are today. So I think we did what we set out to do, and we found so much more that was so incredibly interesting. And I really hope that there'll be more discoveries like this come from upcoming missions, from the ongoing OSIRIS-REx and Ryugu, or Hayabusa 2, that we're going to hear about tomorrow. And I'm really looking forward to lots more in the years to come. Thank you very much for your attention.
Thank you so much, Carol. We got time for some questions. Well, okay, we got one.
Vesta is the parent body of the AGUs, but also of the Vestoids. I'd be interested in hearing if there have been any recent developments in Vestoid research might even link them to the impact phase.
So the one link that was established some time ago by Rick Binzel is that the dynamical distribution of the Vestoids indicates that they're likely 1 billion years old. And we dated the crater to be likely 1 billion years old. So there's a good match there.
Yes, we can have another one.
Yeah, so I think Simone Marchi addressed that in his talk this afternoon. So it's going to be harder to recognize the carbonaceous chondritic components against the background series. And we expect that the organics likely have broken down into amorphous carbon, which is not easy to see. But based on some data that's still in work on the carbon content of series, it appears to be quite carbon rich. So it would imply there is a large contribution both from native series and from the exogenic delivery of material.
All right. Oh, yes. Okay, there's one more question.
What would allow a large spherical body like Ceres to be less differentiated than a smaller distorted body like Vesta?
So, yeah, repeat the question. What would cause a large body like Ceres to be less differentiated than a small one like Vesta? So the difference is the water content. When the ice melts and the water begins to circulate, it very efficiently distributes the heat. So you're able to, there's pentonization reactions buffer the thermal environment, and so the interior doesn't heat up to the point where it drives the fluids off. So the Ceres likely formed a little bit later than Vesta, but the reason why it didn't completely differentiate is we're tying to the original composition.
One more question. Yeah. Oh, back there. Okay. Come forward a little. I'm sorry, there's no microphone in the aisle.
I don't know. It's sort of a weird setup.
Can somebody repeat the question for me?
Something about cryopulverization.
Well, no.
That was
Yeah, can you compare the cryovolcanism on Pluto to the cryovolcanism on Ceres? And I would say, the Ceres, Pluto is a different body, and I think I'm not an expert on Pluto, so I don't see the parallels necessarily.
All right. With that, let's thank Carol again.